in the shockwave model of chondrule formation, a shock front travels through the gas of the protoplanetary disk. Not through the entire protoplanetary disk, that is quite large, but through to individual regions of the protoplanetary disk. Now this shock front might be imagined as a sheet maybe of a certain thickness. Within this sheet, the gas is compressed to very high pressures, and in response there's a very steep increase in temperature. In addition, there is gas particles in the gas, and these are accelerated when they get into the shock front, and this acceleration causes friction, and the friction also contributes to the steep increase in the temperature. Now within the protoplanetary disk, again in regions, there are the chondrule precursor aggregates. So these are hundreds of micrometer sized aggregates of very fine-grained, millions of fine-grained precursor material. Now when the shock front reaches or hits these chondrule precursor aggregates, these are also heated to these very high temperatures above the liquidus and then melt and afterwards cool down again. Now the cooling is a little bit slower than the initial heating due to radiation of the chondrules and also the decompression of the gas. And this allows the chondrules to grow large, up to hundreds of micron-sized crystals inside the chondrules, like olivine, pyroxene, and so on. At some point, the cooling is a bit faster, causing the mesostasis to produce some glass. And also during this stage, there might be some exchange of material between the chondrule, the still molten or partially molten chondrule, and the surrounding gas, causing maybe some sonation in the chondrules, which is also often observed. And now I want to sketch this a little bit, this entire process. So there are these chondrule precursor aggregates here set up to maybe hundreds of microns in size, and then there is the shock front, and the shock front is traveling in this direction. So it's first here, so this might be T1, this might be T0, T2 or whatever, and which means if there's a t-axis, this might be minutes to hours. So this is a very fast process. Now then the shock front is hitting the chondrules here, traveling in this direction, and the chondrules are then heated up to this above liquidus temperatures, which are typically something like maybe more than 2000 Kelvin. So if here's a temperature axis and this is 2000 Kelvin, chondrules are heated up to this very high temperature here. So if there's an initial ambient temperature of a few hundred degrees Kelvin, this is not entirely clear, maybe 500, 600, so this is the temperature in Kelvin. Then the shock front, there's a very steep increase here, and this takes maybe only minutes to maybe hours or something like this. And after shock front, so this is behind the shock front here, there's a first maybe steep decrease again, and then there's a more slowly decrease, as said, due to radiation decompression of the gas. But slow still, if this is minutes to hours, this is maybe minutes to days. So after shock front, the chondrules are cooled down. Now these are really chondrules here, and after a certain time, there are then the cool chondrules finally here. So these are the chondrules here. These are still the hot and molten chondrules, and these are the chondrule precursor aggregates. And as said, behind the shock front here, so there might be some still exchange with the surrounding gas, causing some sonation, something like this. This is illustrated here in this sketch. Again, a little more nicely. So there is the temperature curve here going steeply up and then down here towards this direction, because the shock front is moving in this direction. Cool gas with chondrules, chondrule precursor aggregates, chondrule formation, and these are then the final chondrules. And this is how the shockwave model of chondrule formation works. And it is quite popular because it reproduces this temperature profile that is observed experimentally and is also what we interpret from the petrology and the petrography of the chondrules.